It's remarkable. I mean, it began its journey before we had evolved on Earth. So in the time it took, and that's the nearest neighbouring galaxy. The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years.
Cox explores the enigmatic universe breakers, ancient galaxies detected by the telescope that challenge our current theories of cosmology. Could these colossal cosmic structures hold the key to unraveling the very fabric of our universe?
But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang. Then the Hubble was not sensitive to that light. So that the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies formed.
He also shares some of the latest discoveries by the James Webb Space Telescope that could change the way we've always known the universe.
So one of the things the Webb can do is it can, because of its sensitivity to longer wavelengths, it can see light that's travelled across the universe for longer, and therefore it can see further back in time. I mean, I should say it will acquire lots of data. It's got many missions, and they're all interesting. One of them is to observe the formation of the first stars and galaxies, which is a tremendous problem. We don't really know how the first stars and galaxies formed. We don't really know how those enormous black holes, there's a galaxy called M87 about 55 million light years away, which has got a black hole 6 billion times the mass of the sun in it. 6 billion times the mass of the sun. How did that get there?
Brian Cox shared some remarkable findings made by the James Webb Telescope.
We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang actually. And in that light, before there were stars and galaxies, there are also patterns, which are patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is inflation, which says that before the Big Bang, in the sense that before the universe was very hot and very dense, it was still there, and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. And so there's good evidence for that.
Cox, a particle physicist at the University of Manchester, has an impressive background. He worked on the ATLAS experiment at the Large Hadron Collider at CERN, near Geneva, Switzerland. He's also held prestigious fellowships with the Royal Society and the Particle Physics and Astronomy Research Council. Recently, Brian Cox took to Reddit to answer some intriguing questions from users, and one of the top queries was, what are some of the bigger mysteries that the James Webb Telescope is going to help us solve? Professor Cox responded with enthusiasm, saying, the James Webb Telescope will be able to see the formation of the first stars and galaxies because it's sensitive to the infrared. That's going to be incredibly exciting. He added, it'll also open up the possibility of analyzing the atmospheres of exoplanets. The wild but wonderful discovery would be finding oxygen in an atmosphere, which would look very much like photosynthesis. He continued, there's a lot more, but these are two capabilities that go much further than what the Hubble Space Telescope could do.
The Webb telescope can look at light that's been stretched, much more stretched than Hubble. And if you want to look far out into the universe, which means far, far back in time, then the further out you look, the further back in time you go, and the more stretched the light. And so the Webb is able to look at the formation of the first stars and the first galaxies. It's much more sensitive to the light from the most distant objects in the universe. If you think about it, if you look at something from which the light has been traveling 13 billion years to reach us, let's say, then you're looking at things as they were in the first billion years in the life of the universe. So the Webb, first of all, is going to look at the formation of the first stars and galaxies. It's also powerful enough to look at exoplanets, so planets around different stars. So the Webb is going to be able to look at planets that we've discovered around distant stars and tell us whether the atmosphere has water vapor in it, or is that it would see a planet with oxygen in the atmosphere. So the Webb is tremendously exciting.
So far, Webb has made some mind-blowing discoveries, including insights into the origins of monster black holes and investigating potential signs of life. The advanced technology on board the Webb lets us see things that our eyes naturally can't. Thanks to NASA's ingenious JWST, and with insights from renowned academics like UK's Brian Cox, we're uncovering the wonders of the universe as we delve deeper into space. With the JWST's powerful lenses, Brian Cox explains just how the discoveries made recently can change what we know about the universe. In fact, Brian Cox insists that this new and insane discovery could destroy every idea about the universe we once had. The observable universe encompasses all that we can see, measure, and study with our Earth-based instruments and space telescopes at this point in time. It includes stars, galaxies, and other celestial objects within our observational range. When we refer to the observable universe, we're talking about a tiny fraction of the entire universe that we can currently study and understand. The complete size and shape of the universe remain unknown, but the observable universe is estimated to have a diameter of about 93 billion light-years. To put it into perspective, a light-year is the distance light travels in 1 year, roughly 5.88 trillion miles, or 9.46 trillion kilometers. Therefore, the observable universe spans an astonishing 546.84 billion trillion miles, or 878.58 billion trillion kilometers, a scale that's so immense it's almost beyond human comprehension. The universe began with a Big Bang, a colossal explosion that occurred approximately 13.8 billion years ago. This event marked the birth of the universe and set off a rapid expansion that continues to this day, propelled by mysterious forces such as dark energy. Now, in the wake of the Big Bang, particles of matter began to coalesce under the influence of gravity, forming magnificent structures like stars, galaxies, and eventually planets, including Earth. Over billions of years, these structures grew increasingly complex, resulting in the incredible diversity of celestial objects and phenomena we can observe today. Despite the immense scale of the universe, it's mostly empty space. To illustrate this, imagine shrinking our entire solar system to the size of a quarter. The nearest star would still be the distance of 2 soccer fields away. And this scenario is within just one galaxy, the Milky Way, which is one of billions in the observable universe. You might wonder why we can't see the entire universe. There are 2 key reasons for this. Firstly, light takes time to travel through space. When we observe distant objects, we're seeing them as they were in the past. The farther away an object is, the longer its light has taken to reach us. Thus, looking at distant galaxies is like peering back at time, revealing the history of the cosmos. In the first episode of his show, Wonders of the Universe, Brian Cox takes us on a journey through the origins of the universe and humanity. He goes back in time to explore how stars evolve, comparing it to how the Himalayas were formed. He talks about the 92 elements found on Earth and how they match the patterns seen in stars. In northern Chile, at El Tatito, he shows how the 3 states of water on Earth are similar to those in the universe. He explains how simple elements fuse together to create more complex ones, but heavier elements only form when stars explode in supernovas. In an old prison in Rio de Janeiro, Cox describes the final stages of a star's life, and in the 16:1 mine, he explains how the rarest elements are created. Finally, at the Atacama Desert, he discusses how matter is recycled in the universe and suggests that life on Earth might have come from space. The universe is constantly expanding. To visualize this, imagine blowing up a balloon with dots on it. As the balloon expands, the dots move farther apart from each other. This is similar to how the universe works. Galaxies drift away from each other as space itself stretches. When this happens, the light from distant objects gets stretched too, shifting towards longer wavelengths, which we see as redshift. Eventually, some objects will move so far away that they'll be beyond our observational reach. Given this, it's not surprising that we haven't seen the entire universe yet. The idea of the universe having an edge is a mind-boggling concept that has fascinated scientists, philosophers, and thinkers for ages. There are all sorts of theories about what lies beyond, but the truth remains elusive. However, three main theories stand out. First, there's the theory that the universe goes on forever, with no end in sight. This idea is based on the cosmological principle, which states that the universe looks roughly the same in every direction. If this principle is correct, it implies that the universe stretches on endlessly without a boundary. The second theory suggests that the universe is finite, but doesn't have a clear edge either. Think of it like a giant ball. If you keep going in any direction, you'll eventually loop back to where you started. The third theory is the multiverse theory, which suggests that our universe is just one of many. Imagine a bunch of parallel universes, each with its own set of rules and properties. These universes could be completely separate from each other or somehow connected. The James Webb Space Telescope lets us look further back in time, uncovering unexpected objects from the early cosmos. With its advanced capabilities, it's allowed astronomers to peer into the universe's infancy. And guess what? They found something surprising. In a recent study published in Nature, the JWST discovered 6 massive galaxies that existed between 500 million and 700 million years after the Big Bang. Researchers were only expecting to find small, newly formed galaxies, but its findings were a game-changer. These galaxies are much larger than anyone imagined, challenging our understanding of the early universe. But there's more. Scientists found that these galaxies are as mature as our 13-billion-year-old Milky Way galaxy. Each of these galaxies contains a mass of stars several billion times larger than our Sun. One of them might even be as much as 100 times billion than our Sun's mass. For comparison, the Milky Way has a mass of stars equivalent to roughly 60 billion suns. Its special power lies in its ability to see things invisible to our eyes using infrared light. This allows it to pick up the faint glow from old stars and galaxies that have been around for ages. Essentially, it can take us back in time, providing a glimpse of what the universe looked like at around 13.5 billion years ago. Now here's where it gets really interesting. The universe is estimated to be around 13.7 billion years old, so this discovery has shaken up our understanding. It's like rewriting the history books. These gigantic galaxies, nicknamed universe breakers, have scientists scratching their heads because they defy 99% of the models we've had for the early galaxies. We used to think galaxies started out as small clouds of stars and dust, gradually growing over time. Well, these universe breakers have completely upended that belief. When researchers received the Webb data and high-resolution photos in July 2022, they were astonished. In a recent interview, theoretical physicist Michio Kaku shared that the JWST discovery of the universe breakers could significantly alter our understanding of the universe.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist half a billion years after the Big Bang, that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only half a billion years old. Something is wrong. We may have to revise our theory of the creation of the universe.
According to Kaku, this potential universe breaker discovery could provide crucial evidence supporting the Big Bang theory and offer new insights into the early evolution of the universe. This discovery, which involved exotic objects or phenomena, such as black holes, cosmic strings, or vacuum decay, is fundamentally reshaping our knowledge of the cosmos.
So you think that these galaxies are huge when they're actually baby galaxies. Now, I personally think that the solution to the problem is these are not baby galaxies at all. They're actually monstrous black holes. Black holes that formed after the instant of creation. That's baffling scientists because they don't fit in the normal sequence of the birth of a galaxy. So I personally think that we're actually looking at monster black holes where perhaps new laws of physics are emerging. And again, if you can figure all this out, there could be a Nobel Prize waiting for you.
Using spectroscopic techniques to analyze light across different wavelengths, scientists can gather valuable information about these galaxies, such as their composition, size, and their distance from Earth. What's fascinating is that this groundbreaking discovery wasn't even among the top objectives for the James Webb Telescope. It surpassed all expectations and unfolded much quicker than anticipated. There's even a possibility that some of the objects found might be something entirely different. While most are likely galaxies, a few could be hidden supermassive black holes. The implications are staggering. The known mass of stars in the universe is now believed to be up to 100 times more than previously thought. This discovery is mind-blowing, even if we consider just half of the sample. Meanwhile, the powerful James Webb Space Telescope has enabled an international team of astronomers to make yet another incredible discovery: the oldest and farthest galaxies ever confirmed. These galaxies take us back to a time when the universe was less than 400 million years old, just a fraction of its current age. The light from these galaxies traveled over 13.4 billion years to reach us, as detected by the telescope. Similar to early observations made by the Hubble Space Telescope, the initial images captured by the JWST revealed numerous potential galaxies. Now, through meticulous spectroscopic observations, astronomers have confirmed 4 of these objects. This allows them not only to study the physical properties of these galaxies, but also to accurately determine their distances. Determining a galaxy's distance is crucial in understanding the cosmos. Astronomers achieve this by calculating its redshift. Now, you might be wondering, what exactly is redshift? Well, it's a fascinating phenomenon. As the universe expands, objects appear to move away from us, causing their light to stretch and shift towards longer, redder wavelengths. This effect, known as the Doppler effect, provides valuable information about cosmic distances. While redshift estimates can be obtained from photos taken through various filters, spectroscopy is a preferred method for precise measurements. Spectroscopy breaks down the object's light into its constituent wavelengths, offering detailed insights. Recent discoveries have focused on 4 galaxies with redshifts greater than 10, indicating their vast distance. The Hubble Space Telescope previously identified 2 of these galaxies, with confirmed redshifts of 10.38 and 11.58. However, the James Webb Space Telescope uncovered 2 even more distant galaxies, boasting redshifts of 13.2 and 12.63. A redshift of 13.2 corresponds to a time period roughly 13.5 billion years ago, unveiling ancient cosmic history. To understand how these surveys and images are done, we'll need to look into the JWST Advanced Deep Extragalactic Survey, or JADES. This is an ambitious initiative aimed at providing an unparalleled glimpse into the early universe. JADES was proposed in 2015 by a consortium of instrument teams, forming an international partnership comprising over 80 astronomers and scientists from 10 different nations. This program has been allocated over a month of the JWST's time. Starting with NIRCam, the JADES program dedicated over 10 days to observe a small region of the sky, including the Hubble Ultra-Deep Field. For over 2 decades, astronomers have explored this region using various large telescopes. By studying the field in 9 different infrared wavelength bands, the JADES team made a remarkable discovery: nearly 100,000 distant galaxies, each billions of light-years away. Next, utilizing the NIRSPEC spectrograph, scientists collected light from 250 faint galaxies during a 3-day observation period. This enabled them to unveil the characteristics of the gas and stars within these galaxies and obtain precise redshift values. With these measurements, astronomers can determine the intrinsic brightness of the galaxies and estimate the number of stars they contain. This facilitates a thorough exploration of galaxy formation over time, even in the absence of direct knowledge of their early developmental stages. Understanding galaxies can be as complex as deciphering human behavior. Just as our early experiences shape our lives, the early generations of stars profoundly influence the future of galaxies. We're living in an extraordinary era where the James Webb Space Telescope is leveraging its transformative capabilities to address numerous questions about galaxies. NASA's Deep Space Observatory telescope is reshaping our comprehension of the cosmos and unveiling a trove of new discoveries. Aside from these surveys, researchers might have cracked the puzzle of why a distant galaxy, encircled by an eerily perfect Einstein ring, is denser than expected. This hefty galaxy, spotted by the James Webb Space Telescope, appears to be compressed by a massive halo of dark matter. Einstein rings, first predicted by Albert Einstein's theory of relativity, are luminous halos formed through gravitational lensing. This phenomenon occurs when light from a distant object is bent around a foreground object, situated directly between the distant object and the observer. The light seems to curve due to gravity, but in reality, it travels in a straight line through space-time, which is warped by the massive foreground object. In September 2023, astronomers identified an Einstein ring, dubbed JWST ER1, using data from JWST. This luminous structure consists of two parts: the JWST ER1R, the actual luminous ring from the distant galaxy, and the JWST ER1G, the foreground object that lenses the light from the distant galaxy. JWST ER1R is approximately 21 billion light-years away from Earth, making it the most distant gravitationally lensed object ever discovered. After adjusting for the universe's expansion, researchers estimated that the galaxy formed about 10.3 billion years ago, roughly 4.3 billion years post-Big Bang. Upon discovery, researchers noticed that the lensing object, JWST ER1G, was unusually dense. The size and shape of the ring suggested that it had a mass of around 650 billion suns, which is exceptionally high for a galaxy of its size. A significant portion of this mass is likely dark matter, a mysterious substance that doesn't interact with light, but constitutes about 85% of all matter in the universe. Yet, even with dark matter taken into account, the galaxy seemed too massive for its size. Additional mass is needed to explain the lensing results, the researchers noted in their paper, though they didn't specify what this additional mass could possibly be. A new study, published by the astrophysical journal Letters, proposes an explanation for JWST ER1G's unusual density. A halo of dark matter surrounding the galaxy is being compressed as regular matter collapses into it, resulting in a higher density of dark matter. Our numerical studies show that this mechanism can explain the high dark matter density of JWST ER1G, stated Demao Kong, lead author and researcher in the Physics and Astronomy Department at the University of California, Riverside. This isn't the first true Einstein ring identified by the JWST. In September 2022, a Reddit user used the telescope's data to uncover a perfectly circular ring of light about 12 billion light-years from Earth. JWST has also employed gravitational lensing to capture the most distant star ever detected, and some of the oldest galaxies in the universe. Researchers are hopeful that JWST will help identify more Einstein rings to further test their theory. Here are a few more impressive discoveries made by the James Webb Space Telescope. The James Webb Space Telescope made a significant discovery in the atmosphere of a nearby exoplanet named K2-18b, located 120 light-years from Earth. This exoplanet, which is larger than Earth but smaller than the giant planets in our solar system, orbits a cool star. Previous observations with the Hubble Space Telescope had suggested that K2-18b might be a Hycean world, characterized by thick, hydrogen-rich atmospheres and oceans of liquid water. The recent JWST data supports this hypothesis, revealing an abundance of methane and carbon dioxide while detecting little ammonia. These results are the product of just 2 observations of K2-18b, with many more on the way, said Savas Constantinou, an astronomer at the University of Cambridge. This means our work here is but an early demonstration of what Webb can observe in habitable zone exoplanets. In February of 2023, the JWST surprised scientists with the unexpected discovery of a small asteroid within the main asteroid belt between Mars and Jupiter. This space rock, approximately as tall as the Washington Monument, is believed to be a remnant from the solar system's formation, providing valuable insights into its early evolution. Asteroids of this size are difficult to detect with other telescopes, highlighting the JWST's impressive capabilities closer to home. Scientists recently announced the discovery of galaxies as massive as the Milky Way, seen in JWST's images of the universe from just 500 million to 700 million years after the Big Bang. According to current theories and models, these galaxies are surprisingly large, and the mature red stars within them are unexpectedly old. This finding creates problems for science, as study co-author Joel Leha, an astronomer at Penn State, remarked. It calls the whole picture of early galaxy formation into question. Also, in 2023, astronomers revealed that the JWST had detected complex carbon-based molecules in a galaxy from over 12 billion years ago.
I'm an astronomer, and I found complex organic molecules in a galaxy that was 12 billion light years away from Earth,
when the universe was only 10% of its current age. These molecules, similar to those found in oil and coal deposits on Earth, are attached to tiny dust grains in space. Detecting such molecules has been challenging due to the limitations of previous telescopes. However, Webb really makes looking for organic molecules look too easy, commented Justin Spilker, an astronomer at Texas A&M University, to Space.com. The rate at which the universe is expanding has long been recognized to be accelerating, yet the precise speed remains elusive. The focal point of current discourse lies in reconciling the accurate value of the Hubble constant, a crucial figure for estimating the universe's expansion rate. Presently, estimates derived from models clash with those obtained from telescope observations. The James Webb Space Telescope scrutinized a category of stars called Cepheid variables, renowned for their immense size and brightness, often surpassing the Sun's luminosity by 100,000 times. Cepheid variables serve as a reliable yardstick for measuring cosmic distances, thus aiding in unraveling the universe's expansion rate. However, rather than resolving the dispute, the JWST's data has further entrenched the ongoing contention surrounding the Hubble constant. Additionally, scientists have observed the early stages of the universe and witnessed the formation of a protocluster consisting of 7 interacting galaxies. Discovered by the Hubble Space Telescope, this cluster is the most distant galaxy cluster identified to date. Simulations indicate that it will eventually evolve into one of the oldest and largest known galaxy clusters in the universe, with a mass nearly 100 times greater than that of our Milky Way galaxy. While the Hubble Space Telescope initially detected these galaxies, it lacked the sensitivity to precisely measure the distances between them, despite their alignment along the same line of sight. It's akin to being high above Los Angeles and peering through a telescope. You might see Phoenix, Dallas, and Atlanta, but determining the precise distances between them would be challenging. However, thanks to the James Webb Telescope, we obtained a much clearer picture. According to scientists, clusters like these are exceedingly rare and challenging to locate. Although it's improbable that the JWST will uncover another unique system like this, the forthcoming Nancy Grace Roman Space Telescope, scheduled to launch in early 2027, will enhance our capacity to identify galaxy clusters in the early universe.